Hi, my name is Kruthik Alapati, and today I'll be talking about my Physics 2211 lab about constant velocity. So the objective of the lab was to create a model predicting the motion of an object with constant velocity and compare it to the observed motion of an object appearing to move with a constant velocity. So why is this important? Well, Newton's second law basically tells us that the acceleration of an object is directly proportional to the force of an object. And for an object with constant mass, well, we can simplify this into the formula F equals ma. And for an object with constant velocity, since the acceleration is going to be zero, and the force, we already said there's the net force for this system is going to be zero on the object. So the acceleration is going to be zero, and the velocity should not change for the object. And if the object is truly moving with a constant velocity, there should be no difference between the real-world observation and the computational model, as the net force on the ball will be zero. And this allows us to see if objects do move with a constant velocity, or if there are forces acting on the objects that can cause a change in the velocity. So for my calculations, I calculated velocity here, and I did that using, the average velocity formula, change in position over change in time, and I got this change in I got this final position and this initial position from the tracker app I used, and I got this change in time from that as well, and calculated the velocity to be 0.543 meters per second. And for this lab, since we are assuming that velocity is constant, we can assume that the velocity of the ball doesn't change from that average velocity. So let's go to the tracker app. So here's the tracker app I used to analyze the motion of the ball, right? So I'll play it for you here, and you can see that it's the position of the ball is being tracked over time, and it outputs that data onto this graph, as well as having these the data over here on this chart. And this can be input into Excel to be compared with the computational model, which I'll show you right now. So here we have the program for the computational model that will predict the motion of the ball with a constant velocity. So here's the initial position of the ball, as was in the observed motion of the ball, and the velocity that we calculated, right? So for the forces on the ball, we have the net force equal to zero because there is no net force on the ball, and the velocity is updated by this force, which is zero, since there's no forces acting on there's no net force on the ball. And the position is updated by the change in the velocity, which is going to change the position. And then the program will output the position values and the velocity values onto a graph, and then it'll print the values so that we can input it into Excel. So let's run the program, and you can see how it's predicting the motion of the ball and outputting the data onto these graphs, and as well as these this data that can be inputted into Excel. So let's take a look at the comparison of the observed motion and the computational model in Excel. So here's the graph of the data. As you can see, it's been inputted into Excel, and there are trend lines for it as well. So this orange line is going to be the data from the computational model, and these blue dots are going to be the data from the observed motion. As you can see, the slopes are not very different, and neither are the r-squared values, but there are small differences between the two lines. So what were my observations? Well, when I was observing the ball in real life, the ball appeared to be moving with a constant velocity. So the difference between the model and the observed motion could be due to certain factors, including the net force on the ball was not zero, even though it appeared to be moving with a constant velocity. The force on the ball, the floor the ball rolled on was not even, or there was human error when tracking the ball on tracker. When compared to the data from the computational model, the observed motion of the ball is slightly different. The r-squared values are very similar, but the slope of the observed data is very slightly higher than the slope of the data from the model. And the ball appears to be moving slightly faster than what the model predicted. So for future studies, when repeating the study later, there are a few things that can be done to create a more accurate prediction from the computational model. The first is the model can be adjusted to take forces such as drag and friction into account. And since a soccer ball was used in the future, the experiment can be done with a smoother object, or the model can take into account the shape of the object. And in the future, when doing this experiment, you can be more precise when tracking the ball on tracker to yield better results. So question 1, what if? So if the axes were flipped when analyzing the ball on tracker, the data for the position of the ball would be negative when compared to the original position. This can be visualized by the slope of the observed data being negative. Question 2, what does it mean? Well, it's not possible for us to say how many pushes and pulls are being added together to give zero net force on the ball, but there are many forces that may be acting on the ball, such as electromagnetic force, friction, gravity, drag, etc. And we can calculate the net force on the ball when we analyze the system as a whole, but there's no way to accurately determine every single force on the ball.